Today we're going to talk about proportions in triangles. So the first theorem that we're going to learn, we're actually going to talk about a couple of them today, is the side splitter theorem. So it says that if a line is parallel to one side of a triangle, so we've got right here and intersects the other two sides, then it divides them proportionally. So that parallel line right there is RS. That's the one that kind of cuts through. That's our side splitter. So by splitting that up, and I'm going to go kind of quick through this, but what it's really saying is if we have this two parallel lines cut by the transversal, right, we'd know that due to corresponding angles that these two would be congruent. We know that these two here would be congruent to each other. And we would know that due to angle that these triangles are similar. So I kind of breezed through that pretty quickly. The main point that I wanted to get to was if you have this happen where you have a line that is parallel to one of the sides of the triangle, as RS is, and intersects the other two sides, right? That gives us two triangles. So triangle RQS being similar to triangle XQY. And the reason I bring that up is if we know that those two triangles are going to be similar to each other, we know that the sides are proportional. So it actually kind of gets a little easier than that. I can say that this side QR over, well, we actually don't even need this whole side. We can do just the part of it. RX should be equal to, that proportion should be the exact same as, just on the other side, QS is to SY. So by knowing that those two triangles are similar, we're able to set up these proportions and we're able to solve for these different sides based on the information that we know, because since they're similar triangles, right, we know that those sides have to be proportional to each other. It's going to be similar when we start looking down at the corollary to the side splitter theorem. All right, this one I'm going to breeze even a little quicker through, just kind of explaining it. But what we're saying is if we have three parallel lines that intersect at two transversals, then the segments intercepted on the transversals are proportional. So one way that I like to think of this, because sometimes it looks really confusing compared to the other, if I extended these lines, it would eventually look like a triangle, right? And if I have this line here in the middle, that's parallel to the bottom one, well, what we actually did by just extending those lines and redrawing it was get the side splitter theorem. So just kind of like we did before, based on the information that we know, we're going to be able to set up a proportion that says that AB over BC should be equal to WX over XY. All right. And we could, and we'll talk about it a little bit more when we get down below, we could switch up how that proportion looks actually. That's the really nice part about proportions. But I kind of tend to do it just how they look. So it even looks like the proportion that we ended up setting up in the picture. All right. And then the last one is the triangle angle bisector theorem. So it says if a ray bisects, so this ray AD is bisecting angle A in that triangle, or angle CAB, if I want to be more correct, then it divides the opposite sides into two parts that are proportional to the other two sides of the triangle. So this one has a lot more to do in proving the theorem, and it's something where if you are very interested, we can always sit down and explain it to you a little bit. But the important part is that it works very similar to what the side splitter and the corollary to the side splitter look like. So just like we did before, it's going to end up being that this AC over this part down here, CD, should be equal to, and if we set up the proportion, it'd be AB over DB. And for these, when I look at those, I want you guys to have those. I want you to be able to see that. It gets kind of confusing. It gets a little muddled when you're looking at it, especially using letters as opposed to numbers. So we're going to scroll down here and we're going to try this out on a problem like, we're actually going to start with number 2 because I put these in the wrong order. So what we're looking at here is if I have one of my 3 situations that I have up above, I can go ahead and I can set up a proportion using these different sides. So if you look in number 2, I have one very similar to the triangle angle bisector theorem. So when I go to set this up, I'm looking, yeah, I can kind of follow what this looks like and write the similar thing down. The way that I like to do it is I look at this problem and I say, if I were to make a proportion, it kind of, or I'm going to try to make a proportion that it already kind of looks like. All right. So if I put those 2 lines there, doesn't that kind of look like a proportion I would write? 20 over 16 equals 4 over x. And if you notice, that's pretty much the exact same that we had here, right? We had purple here, red here, red here. So I just did that because I think it's a little easier to see it just by drawing those in, but that would be how we would set that up. So one note is we could actually rotate this, excuse me, and do it a little differently, and I'll show you in a second. Let's actually solve this one first. So from here, right, just like I have my proportions like we've done before, I can cross multiply it. So I end up getting over here 20x equals, should be 48, or excuse me, 64. All right, and then last but not least, I divide to get that x by itself, and I get that x is equal to 3.2. All right, so a couple ways that you can check that. Just to make sure that they are proportional and that you did it correctly. You could do 20 divided by 16 and get 1.25. And then do 4 divided by 3.2 and get 1.25. That's one way to do it. You could cross multiply them. So 16 times 4 is 64. 20 times 3.2, I know I'm typing it out in the calculator, but it should be 64. So those are good ways to go back and check to make sure that your proportion is correct. One of the things that I was saying was that our proportions can be a little different than the ones that I have written. Now, I think that's the easiest because it just looks like the proportion that I'm going to set up already. But you could technically rotate it. You could do 4 over 20 equals x over 16. It's almost like I took this original one and I just rotated it. All right, and if you notice, when we cross multiply, we still end up getting 20x equals 64, which, hey, look at that, exactly the same. So there's a couple ways that you can approach it, but again, I say try to keep it as simple as you can. If they have it kind of set up for you already, just use what they have. In problem number 1, again, same situation. In this case, we don't quite have the angle bisector theorem, but if we go back up, we have our side splitter theorem. So since we have our side splitter theorem, I'm going to do just what I did before. I'm already looking at this and I see that I pretty much have my proportion set up. So I've got 12 over 3 equals 2x minus 3 over x minus 5. Now, even though this one's a little more complicated, that's okay. If we go ahead and we cross multiply this, right, we should end up getting 12 parentheses x minus 5, because we're multiplying by that whole thing, equals 3 times 2x minus 3. And this should be something that's kind of a flashback to algebra, right? We can go ahead, we can distribute that through on both of these cases. So we end up getting 12x minus 60 equals 6x minus 9. And then from here, we can go ahead and we can solve that, right? That's nothing new. So even though the problems look a little complicated at times, they should be pretty straightforward when we actually go through to solve them. So in this case, I'd subtract 6x from both sides. I'm going to kind of move my work up to the top just because I'm running out of room. So I got 6x minus 60 equals negative 9. I'm going to add 60 to both sides. I get that 6x equals 51 divided by 6 divided by 6. Sorry, it's really sloppy because I'm writing with my hand. I'm going to write the answer in purple. So we get that x equals 8.5. And again, you can go back through and you can kind of check that work, or check to make sure that that proportion is correct by plugging in x, and it should still hold true. It should still work out. On these look a little bit differently, so I wanted to look at them in a different situation. And I gave you two examples for a reason. So if we look at problem 3 and problem 4, they look really, 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 really similar, except for one important detail. And in problem 3, right, we've got this 12 that's described by this side. We've got the x that's described by that side. We've got this side, which is 20, and this side right here is 40. All right, so that one's pretty straightforward. That's like what we've been doing before. If you notice on problem 4, this whole side here is going to be 35. So we're not just talking about all the small little parts, we're talking about the whole entire thing. Let me backtrack before I go too far. Let's solve number 3, and then we'll solve number 4. So number 3, again, it's almost set up the exact way that we want to have it already. I can just put my lines under there, set that up as my proportion, and then I can go ahead and solve that. So I got 12 over 20 equals x over 40. I can cross multiply it. I should have done that in a different color. Sorry about that. So I end up getting 480 equals 20x. To get x by itself, I'm going to divide each side by 20, and I should end up getting that x equals 24. This one's a nice, easy one to check, right? If I'm looking here, 12 and x, well, let's look at the bottom one, 20 and 40. To go from 20 to get to 40, I can just multiply by 2. So 12 to get to the other side, you're probably going to multiply by 2 as well, which makes sense that we get 24. Now in problem number 4, again, here's the little different part. We're talking about that 35 as being the whole entire side. That's fine. So when I look here to set this problem up, I have my x, and it should relate to my 8 over there. All right. So I'm going to even set this up like this. And again, there could be different ways that you set it up. I just like doing, well, we could set it up a different way. All right. We could end up doing part, whole. I'll set it up multiple ways. But in this case, we could look at it as the part of the left side over the part of the right side equals. Now, we already know that we're dealing with 35, right, from the right side. And when we talk about that 35, as I said earlier, we're actually talking about this whole thing. So if I want to get the proportional side on the other side, or the corresponding side, I need the entire thing over here. So my entire side over there is going to be, well, 20 plus 8, which is 28. So one way to remember this is, if I'm looking to set this up, and say I wanted to set it up like I did before, right? Normally I have 8x, 20, I should do that in a different color, 20 here relates to this side here. Well, we don't have anything on that side, right? We could technically set that up as the whole thing minus that part that we know, but then that gets way too complicated, I think. So if you notice that when you go to highlight in a line that, hey, I don't have anything that's comparable on that side, that's when you're maybe looking to say, hey, I need to do the entire thing. So again, you could have set this up a couple different ways, right? You could have also said my part on the left over my whole on the left equals the part on the right over the whole on the right. And again, these are going to end up being the exact same proportions. So notice, that's the thing that I wanted you to notice though, is that these two problems were not the same. Because in the first example that we had, we knew part, right? We knew 4 little individual parts, as opposed to on problem number 4, when we knew part, whole. But when you look at it, it still ends up working out kind of the same way. So if you were to go ahead and solve this problem, I'm going to end up solving the one in purple, just because I think it'll end up giving me more room. 28x equals, and again, don't forget you can use calculator whenever you need to. I am right now. And then I'm going to divide both sides by 28. I end up getting that x is 10 in this case. Ooh, that was weird. I end up getting that x is 10. So that's kind of the way that you go about doing this. Again, I think the most important part of this top part is saying, hey, can I identify these situations? I'm not going to ask you to tell me what the side splitter theorem is or explain how the triangle angle bisector theorem works. I don't need you to do that. What I do need you to do is I need you to look and say, hey, I see that I have one of those situations. So I know that I can set up a proportion, and this is the proportion that I'm going to set up. So that should be your goal for the end of the day. Hopefully that you're able to do that stuff. If you are not able to do that stuff, please let us know. Stop by our office hours and we'd be able to help you. Have a good day.